Assalamualaikum. Very good day. Welcome back to my channel. I'm Dr. Awang from UiTM. My course is Optical Communications. So, for the second chapter, second part of the course is about optics. So, let us have a look at the nature of light. Normally, light is described in three ways. One of it is rays, another one is electromagnetic waves, and the final one is photons. Rays actually, when we describe the light as it could be reflected, whether through a medium of mirror or prism. When we talk about electromagnetic waves, we are talking about the wave of having very high frequency and very short wavelength. When we talk about the nature of light in terms of photons, we will describe the light as having a tiny particles and having a photoelectric effect. So, the optical energies in a wave follows narrow path and called rays. Rays obey a few simple rules. The first rule is that rays travel at velocity in a medium. If it's in a vacuum, we called it rays travels in light and is denoted by symbol C. And in other mediums, rays travel at a speed given by this frequency. V is equals to C divided by W. C is actually a speed of light divided by, not W, divided by N. N is the refractive index of the medium. The refractive index of a medium. Because our wavelengths are proportional to the velocity, the ratio of wavelength of a wave traveling in a vacuum to the wavelength of the same wave traveling in another media is expressed by this equation. So it's equals to the C divided by V is equals to actually the refractive index. So what we can say is that the refractive index is a ratio of the velocity of the wave traveling in a vacuum to the wavelength traveling in a medium. Okay? So the rays normally obey a rules in which they travel in a straight path unless deflected by some changes in the medium, for example, the refractive index of a medium. At a plane boundary between two media, a ray is reflected at an angle equal to the plane incident. If any power crosses the boundary, the transmitted ray direction is given by Snell's law. We'll look into the Snell's law a bit later. So this is the index of refraction, or what we call refractive index of some of the materials. Air is having 1.0003, so normally we use air as a refractive index for air as 1, and it is the reference refractive index for other materials. Water, fused silica, silica glass, polystyrene, sapphire, gallium arsenide, aluminium gallium arsenide, and germanium. These are the materials that normally represented fiber optics situation. So how a light reacts when it meets the interface of two transmissive materials that have different indices of refraction, we will see that in this explanation. The Snell's law is given by this equation. N1 sine theta 1 is equals to N2 sine theta 2. So we'll see what is N1, what is N2. Okay. A refractive index model for Snell's law can be shown by these figures. Okay. N1 is representing the first medium, this medium, and for this case it is air. N2 is representing the second medium, which is in this case is water. So if air is having less refractive index than water. Okay, for example, N1 is less than N2. Snell's law predicted that sine theta 2 here is less than sine theta 1. So, angle of refracted is less than angle of incident. By having the angles less than the angle of incident, the refracted beam is actually bent towards the normal. This normal is artificial line in between, making a 90 degree or perpendicular to the interface. Okay. So the other way around, if N1 is having higher refractive index than N2, Snell's law yield that sine theta 2 is greater than sine theta 1. In that case, the ray bend away from the normal towards the boundary, towards the interface. Okay. Now we will look into the refraction and also reflection. Okay, so refraction, if you can see from this figure, this figure, the straw is bent away from the in the water. It looks like it is bent, but it's actually refracted. If you can see here, you can see the refraction here and also the reflection here. Okay, the laser beam is shine into a particle, a blob of water. Okay, so you can see the refraction here and also the reflection here. When we talk about normal line, normal is actually an imaginary line drawn perpendicular to the interface of two materials at the point of incident. For example, for this case, this is normal. Okay, and for this case, this is the normal line. Okay, so the incident light rays and the projected path should be this way, but having a denser material, the light is refracted. These are some of the exercises that can be done for your better understanding. So we will discuss this in class. This is another exercises that can be done. Okay. So the speed of light in free space is reduced in other media. The reduction as light passes into denser material results in refraction of light. Refraction causes the light wave to bend. This can be calculated by using the equation. Okay, the amount of bending or refraction that occurs at the interface of two materials of different density is depend on the refractive indices of the two materials. Refractive index is the ratio of the velocity of propagation of light in free space to the velocity of propagation in light of a light ray in a given material. It's given by this equation. Okay, let us have a look at how the refractive takes place. How the refraction takes place. So refractive index is given by that equation. That is the definition of refractive index. Now, let us look at prism refraction. Different wavelengths respond differently when at a given refractive indices. For example, sine light, which is normally called as white light because they contain all light frequency, is affected as it passes through a material that is more dense than air. Refraction occurs at both air-glass interface, both way. Okay, if you can see here, the refraction occurs here, and also the refraction occurs here. Okay, the interface between air-glass. The violet wavelengths are refracted most, whereas the red wavelengths are refracted least. This is called prismatic refraction. It is this phenomenon that causes rainbows, where water droplets in the atmosphere act as small prisms that split the white sunlight into various wavelengths. So let us have a look. Okay, of how the refraction occurs from the white lights into the prism, and from the prism out into the air interface. Okay, we can see that the white light is filtered into 7 different colors, from red to violet, and red having the least refracted in angle, and violet having the most refracted angle. Now let us look at the basic principle of fiber optic transmission. Okay, total internal reflection. Before we can understand the total internal reflection, we need to look into the critical angle principle of optics. Okay, the core fiber and the cladding are normally both made of glass silica, but differently doped to allow for different refractive index. The idea is to allow light to pass through the core. The angle of light exceeds critical angle and pass through, and not to allow it pass through the cladding. Okay, so the protective jacket is to protect both cladding and core from the external interference. So the critical angle, let us look at this figure. Incident rays, okay, bear with me for a while. So the incident rays is at angle so that the refracted ray goes along the interface. Okay, so when theta 2 is 90 degree, the angle theta 1 is at the critical angle. This defines the angle at which the incident ray no longer passes through the interface but lays on the boundary. Okay, so the critical angle can mathematically be represented by sin theta 1 is equals to n2 divided by n1 times sin theta 2. So when sin theta 2 becomes 90 degree, theta 1 becomes the critical angle. So sin 90 degree is 1, so it left sin theta c is equals to n2 divided by n1. And theta critical can be calculated from the refractive indices of two medium by arc sin n2 divided by n1. Okay. For any angle of incidence larger than the critical angle, Snell's law will not be able to be solved for the angle of refraction because it will show that the refracted angle has a sign larger than 1, which is not possible. In that case, all the light is totally reflected off the interface, obeying the law of reflection. So ideally, there is no light being refracted. All the light is being reflected. Okay? Theoretically. So the light hits the interface at any angle larger than the critical angle. It will not pass through the second medium at all. Instead, everything will be reflected back into the first medium, and this process is known as total internal reflection. It only occurs when N1, the first medium, is greater than N2. It can only happen when N1, refractive index of medium 1, is greater than medium 2. For our case, the refractive index of core should be greater than the refractive index of cladding. Okay, propagation results from the continuous reflection at the core clad interface, so that the ray bounces down the fiber by total internal reflection. We can see here the entrance ray between air and core. The light is actually refracted. Okay, so the light is actually refracted. Okay, at the interface between the core and cladding, the angle theta 3 should be greater than the critical angle of the core and cladding. Okay, so that the light will obey total internal reflection rules. So it can bounces inside the core until it reaches the receiving end. Okay, so here we can see the acceptance cone, in which the angle where the light will be refracted in the core and then will experience reflection, will be having greater angle than the critical angle, so it can bounces in the fiber using TIR, total internal reflection. Okay. So now we look into the numerical aperture and also the acceptance angle. These two important characteristics will ensure the successful transmission of light from transmitter to the receiver. Okay, the numerical aperture is actually a measure how much light can be collected or can be coupled into the optical system, such as optical fiber or a microscope lens. Okay. The numerical aperture is related to acceptance angle, which indicates the size of cone of light that can be accepted by the fiber. Okay, and then we'll experience total internal reflection. Right, numerical aperture is related to the number of important fiber characteristics. Number 1, it is a measure of the ability of the fiber to gather light at the input end. It is also a measure of the contrast in the refractive index between the core and cladding. It is a good measure of the light guiding properties of the fiber. The higher the NA, the tighter or the smaller radius we can have bands in the fiber before loss of light becomes a problem. The value of numerical aperture range is from 0.20 to 0.29 for glass fiber, and plastic fiber generally having a higher numerical aperture than glass, which is more than 0.5 for the calculation part. Okay, next we'll look into the figures. Here, the figure shows a ray entering the fiber at an angle close to its axis. This ray then will be refracted and will later encounter core cladding interface at an angle such that it will be reflected. This is because the angle theta 2 is greater than the critical angle of the core cladding. Okay? What happened what will happen if the light is greater than the numerical angle of acceptance? Okay, we'll see here. If the light coming greater than the acceptance angles, this light then will be having will be reflected, and the angle here is less than the critical angle. So the light will then refracted into the core. So most of the lights which are outside the acceptance angle cone, which is outside the numerical aperture opening, will be refracted into the cladding. Okay. So we can see from this we can see from this experiment, from this animation, how the core cladding numerical aperture plays an important role. Okay. You can see that the lights within the acceptance angles or within the numerical aperture will experience total internal reflection. Those light outside the numerical aperture will be refracted into the cladding. Okay. So since the NA is often used with a fiber in air, where N0 is unity, it is simply equal to sine theta A. However, if the fiber is in other different material, which is theoretically can be, then N0 is actually the refractive index of that material. The NA may also be given in terms of the relative refractive index difference between the core and cladding, which is defined as follows. NA also can be determined by this equation. So few mathematical equation can be used to calculate the numerical aperture. Okay, so these are some of the formula summary that we encountered so far. Okay, so I wanted you to look into these exercises, and please do these exercises before you enter my class. Okay, now let us look at the meridional rays and skew rays. There are two types of rays can propagate along optical fiber, actually three types. One is the axial ray, the second one is meridional rays, and third one is the skew rays. Meridional rays is actually rays that are passed through the axis of optical fiber. Skew rays is rays that travel through an optical fiber without passing through its axis. Okay. Meridional rays have two rays, bound rays and unbound rays. Bound rays propagate through the fiber by total internal reflection in the core along the axis of the fiber. Rays that enter the fiber must intersect the core cladding interface at an angle greater than the critical angle. Unbound rays are not having the total internal reflection, but it is actually refracted out of the fiber core. Normally, unbound rays occur due to the imperfections at the core cladding interface, which will cause part of the bound rays to be refracted out of the core into the cladding. Okay, you can see here the meridional ray pass through the axis. Okay, we can draw here the axis. The axial ray is whenever light interface from air to core at a 90 degree, the light will pass through from the transmitter to the receiver without having total internal refraction. This light is called axial ray, but it is useful for a short distance. For a long distance with a curve and some impurities, imperfection, the axial ray is not a suitable candidate for light transmission. So meridional rays, which obeys total internal reflection, is one of the best ray that propagate from the inside the fiber optic from the transmitter to the receiver. Okay, these are the bound rays. These are the unbound rays. Skew rays propagate without passing through the center of the fiber. Okay. The acceptance angle for skew ray larger than acceptance angles of meridional rays. Skew ray often used in the calculation of light acceptance in an optical fiber. Skew is good to increase the amount of light capacity of a fiber. Okay, so let us have a look. These are the meridional rays and these are the skew ray. Okay, the skew ray, the cross-sectional of a skew ray is like this. Okay, so I conclude this chapter. I'll see you in the next chapter.